Today we're going to talk about hypotheses and hypothesis testing. You'll spend a lot of time going over hypotheses in the scope and methods class, but it's worth spending a bit of time on them here as well. In more colloquial terms, a hypothesis is a tentative statement about the relationship between two variables. It encapsulates a testable implication from the theory we have presented in our work. In our written work, we are often less formal about how we phrase hypotheses. We might say, for example, that on average, women are more likely to vote than men. We can also state hypotheses in more precise mathematical terms, identifying the parameters from a statistical investigation that we might use in a hypothesis test. The hypotheses that we make in a statistical analysis are always about population quantities. We don't need to hypothesize about our sample quantities. We know what those are in our sample for certain. What we don't know is what those sample quantities tell us about the population. It's the population quantities about which we have to make some sort of inference. Getting a bit more formal, we generally have two hypotheses in which we're interested, a null and an alternative. The null is generally a hypothesis of no difference or no effect. It represents the situation in which our hypothesized mechanism is not operative. The null hypothesis is generally single-valued. That is, it represents a specific state of the world. One example would be that the average Canadian IQ is 100. Another would be the null hypothesis for the voting example above. There is no difference in the likelihood of men and women voting. An alternative or research hypothesis is generally one that we are trying to substantiate with data. It identifies the situation where we are right. The alternative hypothesis is range valued, meaning that it takes on a range of values. Generally, this range is from the null hypothesized value to positive infinity or negative infinity, or both. Our research hypothesis generally states a direction of difference, but is not precise enough to identify a particular value. An example here would be that Canadian IQs are bigger than 100 on average. Suppose that the null is that the population mean is equal to 100. If we observe a sample mean that is 110, the difference could be a function of two different things. First, that difference could just be random. It could be that we happened to get a sample that had a mean that was different from the true population value. And if we drew another sample of the same size from our population, we might not be confident that we would get something that looked similar to 110. Alternatively, this difference could be systematic. In this case, even with repeated sampling from the population, we would generally find average IQs that were bigger than 100, meaning that our null hypothesized value doesn't make that much sense. That is, it's not supported by the evidence. Our job, pretty much for the rest of our lives as applied quantitative researchers, is to figure out which situation we're in. Are we in the difference is random situation or the difference is systematic situation? Hypothesis testing is a place where subtle differences in language can be quite meaningful. So it's worth discussing what I think are the right and wrong ways to talk about the decisions that we make regarding our hypotheses. What if the evidence really suggests that the difference between our sample value and our null hypothesis value is just random? In that case, we would not reject the null hypothesis. The other possibility is that we could reject the null hypothesis, indicating that the current evidence is sufficient to rule out randomness as a cause of the difference between the null hypothesized value and our sample statistic. I want to be really clear that we never prove anything with statistics. Because of the uncertainty involved in our inferences, that is, we don't know whether differences are random or systematic, we cannot claim to have proved anything. Proof requires complete certainty. We can prove things with math, but not with statistics. Also important is that we are not accepting the null. Acceptance implies a longer-term acknowledgement that we have happened on to the right answer. Not rejecting the null only indicates that the evidence as it currently stands is insufficient for us to determine that the differences are not a function of randomness. This leaves open the possibility that in the future we could find such differences. Further, we are not accepting the alternative hypothesis for the same reason that we didn't accept the null. Evidence could arise that would lead us to a different conclusion. When we make decisions regarding the null and alternative hypotheses, we could either be right, that is, we could fail to reject the null when the null is in fact true, or reject the null when the null is in fact false, or we could be wrong. We can be wrong in two different ways. We could reject the null when it's actually true. From our example above, we could infer that the sample average of Canadian IQs of 110 indicates a systematic departure for 100, when in fact the average IQ in Canada is really 100. This is tantamount to asserting that our theory is right when it's not. When we make this type of error, it's called a type 1 error. When we make the opposite error, that is, we fail to reject the null when the null is in fact false, we commit a type 2 error. This is like saying that our theory is not supported by the evidence when our theory is actually right. These are interesting theoretical ideas to consider, but we will never actually know if we made an inferential error or not. Knowing this would require knowledge of the true population value, which we don't and won't have. Here's a recap of what we've gone over. When we choose a p-value at which to identify statistically significant results, we're exerting control over the type 1 error. Smaller p-values required for significance means lower chances of making a type 1 error. Generally, if we're using 0.05 as a cutoff, that means that you will on average make 5 type 1 errors in every 100 tests that you do. There are some complications to this thinking that we'll delve into much later, but this will suffice for now. The main tool we use to make inference is the p-value. The p-value gives us a measure of how likely it is that we would observe a result like the one we got if the null hypothesis were in fact true. Note that this test essentially asks us to assume the null hypothesis is true. There are lots of people who bristle at this sort of assumption. In any event, you will often hear a p-value referred to as a probability, and it certainly has properties similar to probabilities. However, some would suggest that it's not, in fact, a probability. And we will generally refer to it as a probability, though personally I'm ambivalent about this terminology. P-values have been gaining in controversy and are often identified as the epicenter for the current replication crisis in science. One reason that p-values are controversial is that people sometimes think they identify something about the strength of the relationship or effect. They do not. Some people think that p-values make a probabilistic statement about the single result in question. They do not. P-values identify the probability in repeated sampling from the population that I would find something that is at least as extreme as what I have found if the null hypothesis is actually true. Notice that the probabilistic statement is really about what happens in repeated sampling. It is not a probability statement about our particular result. There are other methods that might be more interesting, like the false discovery rate, which is the proportion of rejected nulls among all true nulls. And what will almost certainly seem like a contradictory statement, the false discovery rate can be pretty high, in the range of 30 to 50%, even if we're using a p-value cutoff of 0.05. All of this controversy has encouraged the American Statistical Association to put out a statement on the utility of p-values, I paraphrase that statement here. P-values can indicate how incompatible the data are with the specified statistical model. P-values do not measure the probability that an alternative hypothesis is true or that the null hypothesis is false. Scientific conclusions and business decisions should be based on more than p-values alone. Both substantive significance and statistical significance should be evaluated. Proper inference requires full reporting and transparency. Technically, to make appropriate inferences, you would have to identify all of the times that you touched the data, all of the times that you used the data to generate results, and what results you got when you did so. P-values don't measure effect sizes or the importance of a result, that is, the substantive significance. And p-values are only one tool among lots of tools that we have for evaluating models.